put together in one campus in our main Space Application Center. And Professor Yashpal from TIFR Bombay was called to head this institution. So he was our first director. I am 13th director of SEC. So 13 is a very lucky number for me. And here a very rare picture of Professor Vikram Sarabhai discussing something at Thumba with, this is Dr. Abdul Kalam. So both are discussing something. Those days, Ahmedabad and Thumba were the happening places. So Sarabhai belonged to Ahmedabad. His wife, Mrunalini Sarabhai, all of you know, she was a great dancer and a social worker. She belonged to Kerala. So people used to jokingly say that Sarabhai opened one institute in Ahmedabad, that is PRL, another in Thumba, that is because his wife belonged to Kerala. But it was not like that, all of you know, because when we want to launch rockets, it is near seashore. So that's why Thumba was the right place. It is also the magnetic equator, and it is the ideal place to launch satellites or launch vehicles with very less fuel. And here there is a rare picture of Indira Gandhi discussing something with Professor Yashpal, who was our first director, and another gentleman, Professor Chitnis, who was our second director of SAC, Space Application Center. He has just completed 100 years of his life, 25th July. So he is the only surviving ISRO scientist who is aged 100 years. So that is very remarkable that he is still alive and very looking good, healthy and hale at the age of 100 years. So these are all the stalwarts who started India's space program. And Sarabhai used to say that if you want to do space research or technology, first you should know how to use space technology for applications. So it should be application driven, not for technology driven. And that is how the wheel has turned full circle. Today, again, our Honorable Prime Minister Modi Sahib is insisting that all your programs should be application driven, user driven, means users should come forward for some usage of satellite rather than ISRO making satellite and then looking for users. Because in between it happened like that. We went on launching satellite, but there were no users or takers for the satellite. But now today, again, the emphasis is more on having users for the various satellite which we are launching. So this is how we started rocket. All of you know, the rocket parts were carried on bicycle, bullock cart and all that. And Nick Apache, the first rocket, sounding rocket, was gifted to us by France. And we learned how to launch a rocket. All of you know, when during Diwali time also, when we student or they launch rocket, it goes here and there. So we learned how to launch a rocket perfectly. So that is how we launched a sounding rocket on November 21, 63. So that was the starting point of our program. Then we had SITE program. We just completed 50 years this year on 1st August. That is Satellite Instruction Television Experiment. So we hired an American satellite to know how to use a satellite to do TV broadcast. Today you will feel that what is so great in having a TV broadcast using satellite. But those days, you can imagine 1975, 2,400 remote places, rural places in India, they were all connected through this transmission of a TV broadcast program from an American satellite. And those days, why it is important? Because it was the largest mass mobilization program. Those days, many parts of our country didn't even have electricity. That time we could manage this particular big program of 2,400 places linked through a satellite by a TV broadcast program. Then we learned how to use satellite for doing communication, to transmit data from one place to another, to talk from one place to another using another Franco-German symphony satellite. So this was our satellite telecommunication experiment project. And then there was a scientist in PRL, Physical Research Laboratory, known as Professor Pisharotti. So he started this remote sensing experiment. So he used a camera to take pictures from balloon, rocket, not rocket, balloon, then helicopter, then aircraft. From there he took pictures of coconut tree and tried to find out the disease prevalent in the coconut tree from remotely. So that was how remote sensing program started in India. So these were the beginning of India's space program. And today this is what is ISRO. Under Prime Minister, we work under Space Commission, which approves all our program. Department of Space and Atomic Energy, as I was mentioning, they are directly working under Prime Minister's office because that gives us a easy access for all our proposals Either they get approved or rejected, and we get the decision very fast. If it is through any other ministry, then it will take years to get approvals for our program. That's why it is directly under PM, and Space Commission gives approval for all our programs, and then PM approves it. There are 7 major centers of ISRO. SAC is one of them, Space Application Center. And each place has its own ambience, as you can see right-hand side, whether it is Bangalore or Trivandrum or Sriharikota or Mahendragiri near Kanyakumari, or Hyderabad Center here, NRSC, or Dehradun, where we do the teaching for related to remote sensing, or Sriharikota, from where we launch the launch vehicles, or SAC. I have not mentioned SAC. I'll tell you separately about that. And last couple of years, another change has come. Government wants that private sector should play a major role. And students, startup, academia, all these people also should participate in a big way in India's space program. So that's how this InSpace has been created, Indian National Space Promotion and Authorization Center. So it is headquartered in Ahmedabad now. So what we lost with the death of Sarabhai in 1970s, now again something has been given to Ahmedabad with his headquarter of InSpace. And InSpace will work both as a regulator as well as facilitator. So like TRAI, Telecom Regulatory Authority of India, this is a regulator for all our space activity. And PRL, NARL, NESEC, and Indian Institute of Space Science and Technology, where we teach BTech and MTech degree programs. So that is another institute located in Trivandrum. So these are all the autonomous bodies under this. So this is how ISRO structure is there today. Our budget is around 13,000 crore and 17,000 people. So we are static since last 10 years. Our strength is only 17,000 regular employees. But work has increased almost 5 times. So how we are managing it is that now we have more contract people, almost 20,000 contract people. And then we hire a lot outsourcing we do. So we give our activity to private sector, involve a lot of student apprentice and all those things also. So that's how we managed, although work has increased almost 5 times. We are able to manage with same number of people, 17,000 only. Budget 13,000, it will look very big, but actually we can compare it with our defense budget of India, which is 8,60,000 crore. Similarly, Ministry of Agriculture budget is 2 lakh crore. Compared to that, this is nothing. But government cannot give more than this. So that's why this opening up of space sector for private is happening now. But still, despite all this, Chandrayaan-3 and all that, which we are claiming that India has achieved great in space, our share in world market is only 2%, not even 2%. It is only 1.7%. So now government wants that this should increase to at least 5%, if not 10%. So that's why if you want to increase your share or growth, then you need investment. Now government will not give more than 13,000 crore per year. So investment will come from private sector. That's why it is now being opened up and private sector is encouraged to participate in space activity so that we can increase the India's share. So that's why this InSpace has been set up, and there is a new public sector company. We already had Antrix, but that is dying down because of some arbitration issues. So we have set up another new public sector unit, which is known as New Space India Limited. So that is headquartered in Bangalore and Ahmedabad, and that will support all the programs of ISRO. So all projects will now, instead of government directly funding it, it will be through this New Space India Limited, a public sector company. So it has started with an initial budget of 2,000 crore. Now it has to self-sustain its own. So it has to earn its own money. And new policy has come, Space Policy 2023, new remote sensing, geospatial policy, and space data policy. Now data will be available free of cost to everybody. Up to 5-meter data, any researcher, any student, any academia can access that through our Bhunidhi website, and you can have access to that data and do research. And 5 to 1 meter is, some of this data is price data, and below 1 meter it is slightly depending on case by case basis, we give approvals for that. But overall data policy has been made very what we call very transparent and very open. So it is now the emphasis is on open data and open science policy. This is our scorecard. ISRO was set up in 1969, 15th August. So 56 years, 233 missions. But what this doesn't show is that we have our share of failures also. So in ISRO, Space is a risky business. All of you know that. So we don't consider failure as failure. We see it more as a first attempt in learning. FAIL, first attempt in learning. So that is how we treat it. But as I said, there are failures. So this year, our first two missions were failures. So our rocket worked very well, first one, but it didn't put satellite into the right orbit, our navigation satellite. Similarly, the second rocket, it got busted in space itself. The third stage of the rocket didn't work properly, and we lost a radar satellite due to that. So these type of things do happen. But recent one, 30th July, when we launched NISR, that was a big success. This is Space Application Center. So this was the India's first communication earth station, which was built by Sarabhai in 1965-67 time frame. And this is that 14-meter antenna, which was built by NEC Japan. Now, those days it was known as Nippon Electric Company, NEC from Japan. So they took this contract and built this earth station. This was India's first earth station. So in that whole area, this was the only building. The rest all was a forest area. And today in this place, we have 50 buildings. So you can imagine how much growth has happened over these 53, 56 years. And now we have two more campuses, 7 kilometers away from our main campus. So these are these two campuses. And we also have our station in Delhi. And again, it has a heritage value because our Prime Minister then, Indira Gandhi, used to go to this place to address the whole country. So even those days, Prime Minister has to go to this earth station to address the whole country. And we have a very good exhibition. So whenever you come to Ahmedabad, please do visit us. It is worth visiting. And now InSpace is also headquartered in one of these, our campuses. And a technical complex has been set up where student startups can come and do the work. All design facilities are there, testing facility, everything. They are available free of cost to student startups. And even private sector can access all the ISRO facilities. So that is the change which has happened as far as policy is concerned. SAC is a unique center compared to all other ISRO centers which do specific type of work. Either they make rockets, they launch rockets, they do propulsion related activity, or NRSC does only data reception and processing related activity or application. But our center is a multifaceted, multidisciplinary center. So we make rocket works for only 15 minutes. Satellite is like a vehicle which provides power supply and control the movement of the spacecraft. But what does the actual work in a satellite is the payload or the instrumentation or the sensor. So that sensor is developed by us here at Ahmedabad, and the end product, that is application or upyog, that is also being done at Ahmedabad. So we do the major, what we call the heart or the brain of the satellite is being made at Ahmedabad. And you can see our human resources. We have mechanical, electronics, computer engineers, and all type of science people also, geoscience, chemical science, physical science, and biological science. So total strength around 2,000 people, and all variety of people with all domain expertise. So that is the uniqueness of my center at Ahmedabad. So unlike other ISRO centers, which are more specific, dominated by one type of people, we have all variety of people and people from all over the country. You can find all type of people from all states, all union territories are available at Ahmedabad. This is how our remote sensing program started. So we started working on the optical camera system right from the beginning. So we have land and water related satellites, high resolution cartography satellite, oceanography satellites, weather and climate related satellites, which are launched at 36,000 kilometers. They all are low Earth orbiting LEO satellites. And our when we started working in 70s, resolution which we could achieve from space was 1 kilometer. I mean, this whole campus will appear as one dot in an image. But today, I can read the number plate of your car also from space. That is at the height of 500, 600 kilometers. So that is how the resolution has improved. The miniaturization has also happened. And of course, all of you know the optical camera system, they suffer from one basic disadvantage is that when weather is not good or cloud cover is there or sunlight is not proper, you don't get good images like your normal camera. You don't get good focused images. So same problem is there in satellite also. So if weather is not there, and especially in our border areas, there is always rains are there, cloud cover is there. So for that, radar is the most appropriate sensor because radar can do all weather day-night imaging. So you can see. So I have see this is a camera image where you see a lot of white due to cloud cover. You are not able to see what is there beneath this cloud. But once you superimpose a radar image over that, you get all the information related to uh, what is beneath that also. So this is how I have superimposed a camera image and a radar image. So you can see wherever that white spots were there, that also radar can penetrate any cloud and other thing and can see. So that's why how radar remote sensing started. So almost at the same time we started working on that. Radar, all of you know, there are passive sensor, means it only collect energy which is getting reflected from the earth due to the sunlight. So in that spectrum, in microwave region, we try to collect the energy and try to carry out remote sensing using that. Similarly, there are active sensor, means we carry our own transmitters. That is the advantage of radar, because radar carries its own transmitter, so it is not dependent on sunlight. So that's why it can penetrate the cloud cover, even if rains are there and sunlight is not there, still we get very good images. So that is the advantage. So these are different type of radars. I will not go into the details. And there is a new remote sensing field which has emerged. So all of you are aware that navigation signals are always there. There are 100 navigation satellites of different countries. They are always transmitting some signal for navigation purpose, finding out position, PNT it is called, position, navigation and time. Now these signals can be used to do remote sensing, because this signal is anyway there. You just pick up this signal and do remote sensing using that. So that is called signal of opportunity. So that is GNSS reflectometry. So that is a new field of remote sensing which is emerging, and it gives us a lot of data related to soil moisture, wind speed and all these things. So remote sensing which we do. So this is how our radar program started, almost at the same time as our optical program. And again, resolutions were of hundreds of meters initially in 70s and 80s when we have very high resolution radar. So again, we can take images of up to 0.3 meters. So again, I can read a number plate. An advantage in radar is that even at work during day, it work during night also. So all these type of advantages, even if cloud cover is there, even if rains are there, then also we'll have no problems of working with radars. So this is how our radar program has evolved, and I'm happy to say that today we are the world leaders as far as radars are concerned. So India is considered to be at par with USA or Russia as far as radar technology is concerned. And this was our initial days when we developed a first airborne radar, which was a side-looking radar. It was just a real aperture radar, not a synthetic aperture. So this is how we made a display system, and it just were doing averaging and discarding of PRF. So and that way we tried to generate the first images. Then we made a synthetic aperture radar. So when we went to government when I joined ISRO in 1985-86, so that time we made a very big report, and we went to government with a proposal of asking for 500 crores those days, 1985, you can imagine. Europe has just started a European remote sensing ERS program was started then at a cost of around 500 crores. So on similar line, we also asked our government. Then the government set up a committee, and after a few years of deliberation, they said that it is too early for India to start such a big program of 500 crore. So they gave us 8 crore rupees. So this is how we started working on our radar, and they told us to make first airborne radar, that you first fly a radar in an aircraft, a synthetic aperture radar, and then start working on space program. So this is how from 86 onward we started working. When I joined ISRO, so initial days we worked on this airborne radar, and we flew our first C-band airborne SAR on 1992. So it took almost 6 years for us to first develop a airborne radar itself. So this was our, then we improved upon that radar. And then in 2000, so that is initially when we asked in 85, 86, after 15 years, government sanctioned this money and they gave us 300 crore rupees. So that time it was the biggest costliest program ever built by India in those days. 300 crore program was started with this radar satellite. And that is how we started working on our first active radar system, RISAT-1. And it has a multi-mode operation. It has both land operations, oceanographic, and high resolution up to 1 meter. So it has a what we call strip map and a spotlight mode. So this was the parameter. It was working in C band. So C band was a compromise choice, because if you ask military, they will ask for X band. If you ask the agriculture and other forestry and this type of remote sensing people, they will ask for lower frequency, that is L band, S band, this type of frequency. So C band was a compromise choice between X band and L band. So that is how we started working on this 5.3 gigahertz radar. So this was ISRO's biggest satellite ever built those days. And this is the first time it happened. Earlier, our camera used to be some 50 kg, 100 kg camera in a total satellite weight of 1500 or 2000 kg. This was the first time the payload weight was equal to the satellite weight. That means my radar was also weighing around 900 kg, and the satellite weight was also 900 kg. So together it was 1800 kg. So this was the biggest satellite ever built by ISRO. We started working on 2000, and we told government that we will complete within 3 to 5 years. And in between, in 2006, government or our military wanted a radar satellite for strategic purpose. So they came back to us, where is your radar? We said, we are still working on that. We are not ready yet. So then government bought a radar from Israel. That was a small satellite radar, and it was costing us 800 crores. You can imagine, this program was for 300 crore. We bought a radar in 2006. We placed order. It took 3 years for Israel to build that radar, because there is nothing available off the shelf. Once you give order, then only they will start building that radar. So they built that radar for us at the cost of 800 crore rupees. And ADRIN and NRSC and these people worked on that. It was a turnkey project. After that, in 800 crore, we made 3 such radars. So you can imagine the gain you get by doing anything indigenously. So if we use our indigenous technology, जो आज बात हो रही है ना, आत्मनिर्भर भारत. So that is how we worked on that. So at the cost of 800 crores, we built 3 radars, which we bought as a single radar from Israel. So this is how we worked on that. This was a bigger radar, because we took almost 12 years to build this particular radar. So as I mentioned, we started in 2000, and we were ready in 25th March 2012, and we launched it on 26th April 2012. So we took 12 years to build our first this radar imaging satellite. And as I said, today we are the world leaders as far as radar technology is concerned. So this was our first radar, RISAT-1, which was launched on 26th April 2012, early morning at 6 o'clock from Sriharikota. It was the heaviest satellite ever built by ISRO then, 1858 kgs. Out of that, 900 kg was the weight of the radar, and other 900 kg of the satellite. So this was first time it was 50-50. Otherwise, payload is only 100 kg or like that, part of any radar satellite. So this was our first image which we generate in a quick look system. So this was a digital signal processor based system which we developed, which generated images in real time. So this was the image of Ahmedabad, which was collected by our first radar. This is Kakaria Lake in Ahmedabad. And after that, we have not looked back. As I was mentioning, after RISAT-1, which was our first radar, 2012, then we made a dual frequency radar for Chandrayaan-2 also, where we launched L and S band radar. Then this is that 800 crore satellite which we bought from Israel, and it is like a umbrella. This antenna is like an umbrella, so it gets opened up in space. If the antenna doesn't open, then the whole mission is lost. But we were successful. So this was the first satellite we bought from Israel for 800 crore. After that, we built 3 such radars at 800 crore. So during recent operations in Sindoor and all, this radar was extensively used. So 3 radars are taking care of the strategic interest of our country. So like this, we have built now a repeat of this RISAT in 2022. And this is the RISAT-1B is the radar which we lost when our launcher failed this year in May, when the launcher didn't work properly and the whole radar went bust. This is that LNS band NISR, which we worked together with USA. So after we launched this first radar, 2012, NASA and JPL approached us, and then we started working on this NISR, and we took almost 13 years to build this radar. 2025, 30th July, we launched this particular radar. This was our initial first team which worked on this RISAT-1. Professor Kalla was the pioneer of this radar activity in ISRO. So he is the father of our micro remote sensing program, and this was the first radar making of RISAT-1. That time, my colleague Tapan Misra wrote a very nice article covering almost 20 pages. So this was our project director then, Tapan Misra is here. So that is how he gave the full story of how this radar was built in the record time. Of course, I will not say it record time because we took 12 years to build that. But everything, what the striking feature was, everything was indigenous. And various Hyderabad companies have played a big role in that. Astra Microwave, Centum Electronics, all these people, because we cultivated them right from the beginning. So that's how the indigenous industry got developed. And today, they are not taking orders from ISRO. They are so busy with the activities related to defense and other things that they don't have time to do work for ISRO. That is how these companies have developed now. So this was our repeat mission which we did in 2022. And again, similar, it is big antenna, 6 meter by 2 meter. So it is a phased array radar. This is the first time digital beamforming was done. And this was the second mission which we lost this year due to the failure of the launch vehicle. So again, it was similar radar, C-band radar. So these were the radar images. As you can see, the radar images are also exactly same as the camera images. You will make out everything. And it, other advantages, it can do imaging during daytime, nighttime, all the time. So that is the other advantage. So this is the first time we took pictures of Himalaya using a radar, because otherwise camera images doesn't come properly, because Himalaya always there is rain or cloud cover is there, so you don't get very good pictures. So, and this is how the airport at Shanghai, we could take images. So this is the detailed picture of Shanghai airport. So you can see the aircraft standing there at the tarmac of the airport. And military expert can make out which type of aircraft it is, whether it is Airbus or Boeing or McDonnell, MDA, all these things. This is the picture of Kumbh Mela taken by our radar satellite. So you can see how much detailed imaging we can do, up to 0.3 meters. And we are, as I mentioned, world leaders in that. So America, Russia, China, they are all doing surveillance on us, but we are also equally capable of doing surveillance on them also. So that is the capability of our radar system. We have also developed airborne radar system. So this is what in the Kosi River bridge, by imaging over Bihar, we saw towards Nepal and took the image of the Kosi River. This river is flowing in Nepal. So from Bihar, we took image by adjusting the look angle so that we can see far off, even to Nepal. So this is how we worked on all these things. This is the airborne radar system which we built. And the advantage of airborne is that anytime you can fly these airborne systems wherever you want. So we have airborne systems in all type of frequency band, X band. This LNS band airborne was built as a precursor to NISR, where we built this airborne SAR for our scientists to do experiment with the LNS band radar data so that they can learn how to use the NISR data. This is the P-band radar has the advantage that it can penetrate surface also. So you can see beneath. So if some mines and other things are hidden inside the subsurface, you can do detection. So especially anti-Naxal operations and various other mining and other operations, it is very important. This is the first time we did the LNS band radar from aircraft, so that this data was used by our scientists to study how to use LNS band data for doing various applications using NISR. So this is another radar which is used, again active radar, which is used to do oceanographic mapping, so that it can give you the origin of the cyclone. Today, hardly any people die when cyclone come. That is because of this radar, because we are able to predict cyclone when it originates in the sea 15 days before. So we are able to alert all the people, fishermen, all the collectors, so they can vacate the areas. And that's why we know how, whenever it originates from the ocean, it is called cyclogenesis, and the track of the cyclone is continuously tracked for 15 days. So we know where the landfall is going to happen. So all these things feed into our natural disaster management support program. So these are some of the other sensors we have built. Humidity sounder, which gives us the profile, vertical profile of humidity and temperature, which will feed into our meteorological model to predict rain and other. This is that GNSS remote sensing, where the navigation signals are used to do remote sensing. And now we are building a very high resolution radar which can do sub-meter imaging from aircraft as well as radar. There is a problem that either you get very good swath or coverage, or you get very good resolution. So if you want both of them, then you have to use very novel technique like sweep star, which is, and similarly for this type of different techniques are available which can give us both very good resolution as well as very good coverage also. And then we have higher frequency radars also, which we call it sub-millimeter wave or millimeter wave technology. So we are going to develop this telescope, gigahertz telescope or terahertz telescope. We already made 220 gigahertz and 330 gigahertz telescope. And now we are augmenting it to a 1 terahertz telescope, which is used for astronomical studies. And it will be mounted at Henley Leh, which is considered to be the very quiet place for doing this study. And similarly, a G20 satellite has been announced by our Prime Minister, where we will be putting this particular sensor. Now, few things on NISR, NASA ISRO sweep SAR. So this is a new technique where without compromising resolution, you can achieve wider swath. Because radar, as I mentioned, there are problems. Either you get good coverage or swath, or you get good resolution. So this is how NISR was started, and we started discussing from 2012 onwards. So initially JPL came with a proposal that they have a radar which they want to put it in Indian satellite and India will launch it. But we didn't agree to that. So you can imagine, we have the audacity to say no to JPL and NASA, which was the world #1 laboratory and world's #1 space agency. But India said no to them. Why? Because we were not gaining anything due to this particular deal. So then we agreed on making 2 radars. So one radar was built by us and another radar was built by JPL. So these 2 radar, they built a L-band radar, we built a S-band radar. Both the radars were integrated together, and it started as a L-band radar proposal from JPL, and then finally it ended up as a L-band and a S-band radar. So with this way, directly what we call science-driven mission, and this is how it looked like. It is a very big antenna, 12-meter diameter antenna, which is hanging on a boom of 9-meter. So deployment of this antenna is also a very difficult and challenging task. And this was the work sharing which we agreed to. So satellite was built by ISRO, then L-band downlink by NASA. Similarly, S-band downlink will be by ISRO, and science will be done jointly. We will be launching it, and S-band was built by us, L-band by NASA or JPL. And this was the specification. So it works at a height of 747 kilometer, and it can achieve very high resolution up to 3 to 5 meter with a coverage of 240 kilometers. No SAR in the world has so much wider coverage and such a high resolution. So this is the sweep SAR technique. So what we do is that when we transmit, it will be a very wide beam. So it covers a very large swath. But when we receive the signal, we do it module by module wise. So we do what we call digital beamforming. So we integrate the data received from each TR module and then form a digital beam to achieve the higher resolution. So there were 24 TR modules in L-band SAR, and our S-band SAR had 48 TR modules. And we have both polarimetric and interferometric modes. So that is the advantage of this interferometric mode, is that whole world is looking forward to this particular radar, especially in L and S-band, because it can do what we call land deformation study. And all the scientists are very hopeful that this interferometric and polarimetric mode will give us some clue that future, like we are predicting cyclone, but still we are not able to predict earthquake. So somebody may do some research, find out some technique using this L and S-band interferometric data to predict in future earthquake also, which is a very rare thing to do. So everybody is very hopeful. Of course, it is too early days to say that something will be done using this data, but people are very hopeful, scientists especially, that using this L and S-band interferometric data, someday some technique may be developed, especially using AI and all, that we will be able to predict earthquake also in future. So that is the advantage of this particular type of mission. So these are the specification of that. I will not go into the detail, but I'll show you some of the pictures. So this is how this radar is moving nowadays, 30th July onwards. This is the S-band SAR which was built by us. And this is the radar. Below you are seeing that. And it get integrated with this antenna, which is built by an American company called Astro. And it has major applications, especially in land deformation studies, ecosystem structure, cryosphere, oceanography. So it has wide-ranging applications. And the main interest area is prediction of earthquake or landslide deformation. So that is going to be major area. And this is how the whole radar looks like. So you can see how gigantic this radar is. And it is the costliest radar ever built by anybody in the world. 13,000 crore is the overall cost of this particular. So this is the S-band radar which was built by us at Ahmedabad. And right-hand side, both the radars were integrated at JPL. And this is how the integrated radar looks like. So this is when we flagged off this payload from Ahmedabad. It went to JPL, and then it was integrated at JPL with the L-band radar built by JPL. And then when our chairman went there, we flagged off on 4th February 23. This radar, these are two radars together, stacked together. It was sent back to us here at Bangalore, where it was integrated with our satellite. And this is how the time frame. We took almost 2 years to make it ready after integration. And these are all the pictures related to that. And this is how the deployment took place. When we launched it, after that immediately we didn't deploy the antenna. It took almost 10 days for us to do the deployment of the antenna. How? Step by step, because NASA didn't allow us to, left to us, we would have deployed it within 2 days. Our people were very confident, our satellite people. But NASA was not ready to take that risk. So they dictated that we should do it step by one arm of the antenna was deployed. And then finally, this reflector was unveiled. And this is the 12-meter antenna, which is now working very well. And this is how it looked like in the fairing. So it is our GSLV with a 4-meter fairing. So before this, the condition was we should have 3 successful missions of GSLV. Then only we will be able to fly NISR. So these are all the conditions which we agreed to. This was our team which worked on S-band SAR. And now the data products are being generated at NRSC. And it will be available free of cost to any researchers, whether it is a student or any other researchers. So data dissemination will happen from NRSC Hyderabad as well as Alaska facility from USA. So whole world, anybody, any researcher can get this data free of cost, and various science and applications have been worked out. Very potential activity related to all these 4 fields have been worked out by people. And right now calibration and validation plan has been worked out. So we have launched it on 30th July. So next 3-4 months, we'll be doing extensive calibration with internal as well as external calibration by deploying various point targets and other things. And before that, we made our algorithms ready with our other radar data of RISAT-1. And this was how we organized almost 10 science meets before this. So all these years, every year we used to have science meet where our scientists from both the countries were working together and working out the plans of how to use this NISR. As a precursor to that, we use that airborne SAR data also. And this is how it was launched. In next 5 months, up to March 2026, we'll have very detailed calibration, and then data will be available to all the researchers. So these were the first day images which we got from S-band radar. There was equally similar L-band radars also available. So this is Rani Khet in Uttarakhand, then Haripur Dam again in Uttarakhand. This was the polarimetric image we got on 19th August in Uttar Pradesh. It is the Ganga River. And similarly, this is the Delhi image of hybrid polarimetric. So these are not yet released, but these were the first day product, because we are looking forward to the top people in both the countries releasing these particular products. So initially, studies have been carried out by our scientists to work on this. So these studies are going on with all the people, and we are hopeful that whole world will be very eager to use this data. And as I mentioned, the land deformation studies are going to be the major area where. Now, just briefly to tell you about what two will be doing after Chandrayaan 3. So this is how Chandrayaan 2, we failed to launch land successfully during Chandrayaan 2 times. And but we launched a very high resolution camera. So what Neil Armstrong left behind in 1969, we were able to take image of that on 2021 after 52 years. So you can imagine everything lying as it is, because there is no atmosphere on moon and there is nobody to move it here or there. So what Neil Armstrong left behind when he came back on 20th July, it is lying as it is. Apollo 11, similarly, Apollo 12 also left behind many things which are still visible with our high resolution. So this is the highest resolution camera by India, 0.3 meter. It is doing imaging over the surface of moon also. Last time when Chandrayaan 2 time we failed to land, that time we immediately within 2 hours we came to know that what happened. Our lander crashed landed, and it landed 482 meters away from where it was supposed to land. It was supposed to land here, it landed here, it was broken into pieces. So this, our camera could capture that image. That time our Prime Minister was there, he was consoling our ISRO chairman. That time everybody saw this on TV also. Then we started working on Chandrayaan 3, and we take almost 41 days to reach moon. Why we take 41? Because our launcher has limited capability. It can carry only 4,000 kg weight. So we do in an innovative way. We try to launch our satellite. So we go out of the Earth influence, then go towards moon, and then enter the moon influence. And took almost after launch, we launched it on 14th July, and we reached there on 23rd August. That means we took 41 days to reach there, while USA, China, Russia can go within 5 days to moon. But we do it in our own innovative way. So it was similar to Chandrayaan 2. There was not much change. That day we were in Sriharikota and our minister was also there. That day people felt that as if we were on moon, but actually it was only the launching of the satellite. That there was another 41 days still we had to go. That time our chief minister came at Ahmedabad to see this launch, landing of that moon. All our scientists were in various auditoriums, and all of you saw this scenario when our moon landed, lander landed on moon. And this was the contribution of my center. These were all crucial contributions, because all camera system, radar altimeter, which gives the height when lander was coming down, then the hazard detection and avoidance processing. So that is in real-time processing, signal processing, everything of this camera images is being done by this system, computing system, and it controls the movement of the lander. So our system, and we selected the landing site. For 7 years, our scientists worked on various images of moon and find out where to land. Site number 1, then alternate site 2. If we land on 23rd August, where we'll land. If we land on 27th August, where we'll land. So all these things were done by us. And this is how when we landed there, NASA captured this image of Lunar Reconnaissance Orbiter, their own camera system, and they took the image of that point where our lander landed. But NASA image is not that good. You see our image, which our camera took, how clear it is, because our camera image is a very sharper image of 0.3 meters. So it is exactly telling you where the lander landed. And this is our camera took image, rover took image of the lander. And now we are celebrating 23rd August every year as a National Space Day. Then we launched a Sun mission also, and next 5 years, this will be working from 2023 to 2028, because these are the highest solar sun cycle years. Lot of activity, solar activity is going to happen during 2025 to 2028. So this will be captured by this Aditya mission. And after Chandrayaan 3, what? So we are going to launch what we call a moon return sample mission. So where we'll go to moon, we'll launch 2 satellites. One will go there and land there. Another will be orbiting around moon. So the fellow which is landing, it will collect soil and rock samples, and the propulsion module will come back, and it will get docked with the orbiter which is moving around moon. So it will dock with it, and then whole thing will come together back to Earth. And out of that one module which contains the soil sample, it will re-enter the Earth atmosphere because everything cannot re-enter. Otherwise, it will get burned out. So this particular module, which is a typical heat shield around that, it will re-enter the Earth's surface and it will bring back the soil samples from the moon surface. And then we are doing a joint mission with NASA, JAXA, that is Japanese Space Agency, which is called Lunar Polar Exploration. So last time we went up to 69.3 degree. We didn't go exactly South Pole. Although we told we have gone to South Pole, it is 69.3 degree latitude. This time we'll be going exactly at 90 degree, means exactly at the tip of the South Pole, along with Japan. So Japan will launch the lander. ISRO will make the lander. Japan will make the rover. So this rover, our current rover was only 30 kg weight. This rover will be 350 kg. And it will go, as I mentioned, it will land with a precision of 1 by 1 kilometer. Currently, 10 by 10 meter. Currently, our precision was 500 meter when we landed in Chandrayaan 3. And our area of landing was 4 by 2 kilometer. This time, we'll be landing in a very precise way. In a 1 by 1 kilometer Medan, we'll be landing. And it will be a 7-day mission. So 7 moon days. So 1 moon day is equal to 14 Earth days. So 98 or 100-day mission. Last time it was only 1-day mission. If you remember that after 14 days, the lander and the rover didn't work. So because it was meant for only 1 moon day, that is 14 days. This time it will be after day, night will happen on moon. So that time temperature goes up to minus 150 to minus 200 degree. Still it will survive that temperature and then again it will get revived when day comes. So this is all how we have planned this mission along with Japan, and it will be launched. So we have different these ground penetration radar, Doppler radar are part of that. Then we are going to Venus also. We'll put an orbiter around Venus. And we are studying Venus so that Earth cannot become Venus-like. Why we are studying Venus is because due to climate change and all these changes which we are seeing on Earth, someday Earth may also become like Venus. So we have to protect our planet from that. So that's why this mission is important. Similarly, Mars, we have already done MOM-1 mission. And now we are going to do what we call a Mars landing mission. So this time we'll be landing on Mars. Landing on Mars is easier. It is surprising, but many of you may be aware that because there is a thin atmosphere on Mars, it is easy to land using parachute or a motored vehicle. But what is difficult is that because going to Mars, it takes 10 months. And then if I press a key, any command I give from here, Earth, it takes 15 minutes to travel to Mars. And then another 15 minutes to get back the status, what has happened. So after 30 minutes only I will know what has happened. So that is the challenge involved in a Mars landing mission. And right now we are doing Gaganyaan. All of you know that we are going to put a Gaganyatri or astronaut. Mr. Sudhanshu Shukla has already traveled in International Space Station. Our Gaganyaan will be going there for 1 to 7 days at the height of 400 kilometers. It will orbit around Earth for up to 7 days and then come back on Earth. And the requirement is all 100% of time we are in touch with the astronaut. That is the biggest challenge. Right now with all the capabilities which we have, we can achieve only 40% communication. So from 40 we have to move to 100. So we will be contact with astronaut all the time using email, internet, voice communication, video communication. So that is the challenge. So we are doing a lot of tests so that we can safely bring the astronaut back. Then we are building like International Space Station, our own Bharatiya Antariksh Station. So where we will be having 5 modules and it will be integrated in space. So these 5 modules, so it is like building a house in space. So we'll send one by one these modules. So we'll start from 2028 and every year we send one module. By 2035, we'll be completely building this house and this station will be used as a transit point because our Prime Minister has already announced that by 2040, we'll be putting man on moon. So for that, this will be used as a transit point, like a guest house. So first our astronaut will go to this guest house in space and from there it will go to moon by 2040. So these are all very ambitious and tall tasks, but hopefully we'll be able to do that. So as a precursor to that, recently in July, we sent our Sudhanshu Shukla. He went to this Axiom mission to International Space Station. So with the Dragonfly, and this is how the whole mission was. It took almost 28 hours to go from here to 410 kilometers and dock with the International Space Station. And this is how they docked. Then they already 7 astronauts were there, those in white, and these 4 entered there. So total 11 astronauts were there together at ISS, and they did experiment for almost 20 days. He was there, and June 26 it was launched, and when July 15th he came back. So during that time, so initial 3-4 days he was really having very bad health, because he was having a lot of nausea and vomiting and all those things, and then he was very difficult in passing urine, stool, everything. So that is how microgravity is. When you get launched, you have a gravity 4 times what on Earth. So on Earth we have G gravity, 1G, that is 9.8 meter per second square. Once you are launched, immediately you get a pressure of 4G. But since you are wearing the space suit and all, you are able to survive that. Otherwise, your whole lungs and body will get broken into pieces at that 4G. Then when you enter the space, it will be microgravity, that is 10 raised to -5 gravity. So this is how the challenge is when going to space in the microgravity environment. So he talked with our Prime Minister through video link and talked with our mission team also. And then he came back, he did a lot of experiment on microgravity, bacteria growing and growing some microalgae and all these things. So these 7 experiments were done. And finally on July 15th, he came back at California beach after spending around 20 days in the whole mission. And we spent around 550 crores on this mission. So it was not a free mission. India paid so much money to NASA and Axiom, Elon Musk, for doing this experiment. And this is what I was mentioning. This year's Nobel Prize 2024 physics, John Hopfield is considered father of AI. And chemistry also, Dennis Hassabis and John Jumper. So they worked on ANN and AI model. So they are all computer scientists. So they are getting prizes, Nobel Prizes for physics and chemistry. So that is the change which is happening in the world. I mean, the AI is percolating everywhere in the world, in all your fields. So we are doing AI for doing various remote sensing, data processing, and other activity. And this is how the Kumbh Mela images, we enhanced the image using AI techniques. Then this is how we generated a super resolution out of the radar images. And earlier we used to generate traditional data products, but now the trend is towards what we call analysis ready data. It's like a cooked food. Immediately you can apply your algorithm and do processing. And now trend is towards AI ready data. Means you can directly apply your AI algorithms onto this data. So data will come to you in that form so that you can directly apply these algorithms. And it is like a cooked food we get in the market. So we do various applications using this. All type of missions are being carried out at various levels on various themes, whether it is ocean, water, geoscience, climate studies. So we have these 2 very good websites. So any interested people can go to this Vedas and Mosdek website. And we are also doing some activity on what we call the quantum communication. A lot of cyber frauds are happening. So that will be thing of the past when this your OTP, which is coming on your mobile, when you do any financial transaction, so that is getting stolen, and that is due to which cyber frauds happen, or your account getting hacked. So these all will be things of the past when we use quantum communication. So photons of light will be used to transmit your OTP. So nobody will be able to do theft of that. If somebody tries to do theft, then automatically communication will stop. So that is the revolution which is going to come. So ISRO is going to launch these 2 satellites, LEO orbit satellite and 1 GEO satellite, to do this communication all across the country. So we can transmit all the financial transaction as well as the stock market transaction will happen through this quantum communication. So nobody will be able to do any fraud using that. And then we are developing a quantum radar. Quantum radar is, see, today your radars are not able to detect some of the stealth target, but this quantum radar can detect any type of aircraft. Even if it is a stealth target, that also it will be able to detect. So that is the advantage of having this quantum technology. So future is space tourism, which has already started in USA and Russia. Space station, which is already there, ISS. India now is going to build its own space station. The quantum communication also, world has started. And then we have colonies on moon, colonies on Mars. Today it looks very fictitious or imaginative, but tomorrow it may have become a reality, because all these things we have not thought of earlier. Even your mobile, nobody thought about that. if you can run this, this is a very interesting one, how a space shuttle is flying in over, one astronaut is doing symphony, and with back, यहाँ पे click कीजिए, there is a video here.
Welcome aboard the Dragon spacecraft. I'm Sarah
This
Gillis, one
from
of the
World
flight
5. So there is a team at California, Los Angeles. There is another team at Haiti, another at Sweden. All are getting synchronized from space to Earth. So this is how world is going to be unified with space. So remote sensing, navigation, communication, science. So as I mentioned, Gaganyaan, Chandrayaan, Mangalyaan is only 25% of activity we do. Rest 75% is what I told you today, which is what ISRO is doing. Thank you for being patient.
Thank you, sir. Thank you so much for your insightful session. We have learned a lot about the journey of ISRO, the space, the sensors, different kinds of sensors, Chandrayans, and the future upcoming projects, and that will make our country very proud. And it is very happy movement too. When I was seeing the PPTs, it was all recalling the proud moments of our India. Thank you so much, sir. Thank you so much. Thank you all. Now we'll have a lunch break. I request everyone to please have lunch at the counter. And the coupons will be given at the counter. Please enjoy the lunch. Thank you so much. Thank you all. This is all. We conclude the day one by this. See you all tomorrow. Thank you.